Okay, this is with GOT chapter 20. It is on conventional energy alternatives. So 19 was basically on fossil fuels and energy. And then this is alternatives to fossil fuels, but ones that are considered more conventional, so not like new type things. The case study is on Sweden, and it talks about Sweden trying to free itself of fossil fuels. They wanted to move to renewables. They did have a strong nuclear program, but actually after Chernobyl, they were very concerned about the nuclear fallout because the prevailing winds blew a lot of the Chernobyl fallout into Sweden, and their nuclear radiation detectors detected the radiation before Russia had actually released that there was an accident to the public. And so they kind of like broke that story. And so people were very anti-nuclear after that, and they decided that they wanted to divest themselves of nuclear power. And this whole part is about, are they going to be able to do that? Then you get to section 20.1, which is about alternatives to fossil fuels. So there are some things that you should know. You should know about the world energy supply by source, and then you should know about the world's electricity generation by source. So the world energy, you should know, number one is oil, right? Oil is still king. Then two is coal, and then natural gas and bioenergy. And when we're talking about energy here, we're talking about energy that's used for everything. Transportation, heating, just things other than just electricity that people need energy for. And then electricity is just electricity, what comes out of the power plant. And in terms of electricity generation around the world, coal is king. Still coal, 38.4% as of, I think this was like 2020 or something like that. Natural gas is on the rise. It is number 2, then hydropower and nuclear. Move on to the next page. There's a lot on these 2 pages that we need to talk about. So you should know this figure and caption up here, which is about U.S. energy consumption by source. So again, this is energy, not electricity. So it could be related to transportation or things like that. And so we've got oil at the top because of transportation things, natural gas. A lot of buses and things like that do run on natural gas, and then we have that in terms of like industrial applications, and a lot of power plants have switched to natural gas and coal. And you can kind of see here on this chart that coal went up and is now going down. It's this orange line. Oil went up and stayed pretty constant for a while there, and then natural gas has been booming. And then these 3, nuclear, hydro, and bioenergy, going up a little bit down here. So we get to section 20.2, which is about nuclear power, our first alternative, conventional alternative. One of the important things to note about nuclear power is that it has no greenhouse gas emissions or air pollution. So it is considered a very clean energy source in that respect. So let's talk about, what does this mean, nuclear power? What's going on? We're talking about nuclear fission here. There's 2 types of nuclear reactions. There's fission and fusion. Fission is when things split apart, like you learn in biology, like cell division is called fission. So this is splitting apart of atomic nuclei. So the heavier elements on the periodic table, like from lead on up, tend to have unstable nuclei, and they split apart. The one that we use for power generation is uranium, specifically the isotope uranium-235. This is what's used in nuclear power plants. And what's happening here is that we bombard this piece of uranium-235 with a neutron. And the one neutron causes the nucleus to split. And then in splitting, which will kind of go up to this picture up here, in splitting, so a neutron bombards the nucleus. And then in splitting, it breaks apart into 2 smaller atoms, and it can be different things. In this case, they're saying krypton and barium. And then it gives off a lot of energy in the split, and then some free neutrons. And so these free neutrons can then go bang into more uranium nuclei, and then, which is what's happening here, these free neutrons then hit other atoms, which then split, and this thing keeps going and going and going. So it's called a chain reaction, or a positive feedback loop, because as you can see, you get more neutrons out than you put in. And so one neutron can break apart this nucleus, get energy, you get 3 neutrons, which can break apart 3 more nuclei, and so on and so on. And so you get an explosive chain reaction. So what you want to do in nuclear power is control that. And so we'll talk about that in a minute. Then we need to talk a little bit about the uranium. So mined uranium is generally in the form of uranium-238 instead of the 235 that it needs to be for power generation. So it must be what's called enriched. Underline that. Enriched to uranium-235. And basically what that means is they just kind of distill it to separate out the heavier 238 from the lighter 235. This uranium-235 is then formed into small pellets, and those pellets are made into fuel rods. The fuel rods in the power plant are stored in water to prevent explosion. And then next to them are things called control rods, and the control rods are made of materials that absorb neutrons. Okay, so we're looking at this picture right here. This is the containment building. This is where the nuclear reaction is happening. So here we've got these little pellets of uranium, and that's what we would call the fuel rod. You can see that there is water in here, right? This is a closed loop of water right here. And so this uranium will heat up this water, and then it will send heat out into here, but this water and that water don't come into contact with each other. So this outer water doesn't actually get radiated, it just gets the heat from this pipe. So this pipe will heat up this water, that water will turn into steam, it's called the secondary loop versus the primary loop, and then that steam will turn the turbine that we've talked about so many times. These right here, in between the fuel rods, are what are called the control rods. And those are the things that are made out of the substance that absorbs neutrons. So the control rods can be raised or lowered depending on how fast they want the chain reaction to go. So we're talking over here about an uncontrolled chain reaction causing an explosion, but you can control this chain reaction by lowering the control rods in between the fuel rods. And so then they're absorbing these extra neutrons. And so you get maybe one of the 3 that goes on to hit a nucleus. And so you just get a nice linear chain reaction going on here in the reaction chamber. And so that's kind of what this is talking about here. The control rods absorb the neutrons. So the reactor core is housed, this is the reactor core, housed in what's called a containment building. And the containment building is built with like meter thick concrete walls and then steel walls around that to prevent radiation leakage and then any sort of leaks, like if there's a natural catastrophe like an earthquake, which we will talk about more later. Then if you kind of go here, at this point, it's exactly like any other power plant. You have the turbine turning the generator, which makes the electricity, which goes out into the transmission system. And then you have this water, which does not ever really get irradiated. The radiation is kind of contained over here. This is just heat that comes out. And then this heat heats up this water. And then this water gets dumped into the cooling tower or sometimes back out into like a lake or the ocean or something like that. So you should understand and know what all the different parts of a nuclear power plant are. Specifically, what these fuel rods are made of, the fact that they're the control rods, and so on. Then we move on to page 566. And on 566, we have this table right here, which is the top producers of nuclear power. And you can see that the U.S. is one of the top producers of nuclear power. And then we have France as number 2. But generally, people tend to think of France as like the biggest nuclear state because the percent of electricity that they get from nuclear power is almost it's almost 72%. Whereas the U.S. makes the most, but it's only 20% of our power grid. So the U.S. consumes the most, but we also use the most electricity. And so it's just really a 1/5, a fraction of what we produce. And then France, the nuclear makes up the highest percent of their electricity. So France is really known as kind of being on the cutting edge of nuclear power. And then it gets into this idea of half-life. And we will do half-life energy math problems. You'll talk about half-life. But half-life is defined as the time it takes for half the atoms in a sample to give off radiation and decay. So for uranium-235, the half-life is 70 million years. And so you can see that that means it doesn't go away in a short amount of time. And so that is part of why people are concerned about this idea of radioactive waste. Because if we go back and look at this, there's something called spent fuel rods, which we'll talk about more. But over time, there won't be enough uranium-235 in these fuel rods to really sustain a chain reaction, and they'll be called spent. There will still be a lot of heat and energy inside them, but it's not enough to run this power plant. And so they'll be taken out and replaced with fresh fuel rods. But there's still a lot of radiation and energy and uranium inside them. Okay, so going back to this. And so that's kind of one of the things that people are concerned about when they look at nuclear energy, is this idea of waste. Then it talks about nuclear fusion and that it remains a dream, and I think it will always be a dream. I'd like to think that we would get there. I just have no idea if that will ever happen. But what you should know about nuclear fusion is this is what's happening in stars. The sun's energy, it seems like basically endless. So what happens is you have hydrogen atoms, deuterium and tritium. They are different isotopes of hydrogen. They run into each other. And at a very, very, very high temperature, which is a lot of energy, they will combine and they will give off a neutron, and then these two will combine into a helium atom. So this right here, the red represents a proton, so one proton and one proton, and then over here, the helium atom has two protons. It's been fused together into a new atom. That is nuclear fusion. And in that process, it gives off, it takes energy for it to happen, but then on the other side of this, it gives off a tremendous amount of energy. You actually get more energy out of the reaction than is put into it. And that's why it is so appealing, and people want to try to do that on Earth, because you get out more energy than you put in, and so it would solve all of our energy problems on Earth if we could do fusion. Additionally, there's no pollution involved in it, but it's just really difficult to do because this part of it happens at extremely high temperatures, and they haven't really figured out a way to replicate that on the surface of the Earth. Then we're talking about nuclear power and accidents. You need to know what happened. You need to know the 3 major nuclear accidents that have happened. So the first one was 3 Mile Island in 1979. This was in Pennsylvania in the US. There was a meltdown that was contained, and they think that there were really no significant health impacts. So it was this little island in a river. The plant is actually on an island in one of the big rivers in Pennsylvania, and it had a partial meltdown, and it was mainly due to kind of some operator error, but they got it under control, and the damaged reactor was shut down, and it's being cleaned up. And as far as we can tell, it doesn't seem like there have been any really significant health impacts in the residents around 3 Mile Island. The next one you should know is Chernobyl. Not so lucky in this case. Chernobyl was 1986. It's in what we now call Ukraine. At the time, it was still the USSR. And so that was also part of the problem, is that there was a lot of secrecy from the Soviet Union. And so a lot of time, we don't know to this day a lot of what went on. In Chernobyl, explosions destroyed the reactor. So that reactor that we were talking about a few pages back actually got destroyed. And for 10 days, radiation was escaping the plant. Lots of people died, not as many as like you would think, but dozens of people died. I can't remember the exact number off the top of my head. And then there were a lot of illnesses. A lot of people, there's been a high incidence, it says 6,000 plus cases of thyroid cancer. So what you should know, the number one health effect from radiation is that it causes thyroid cancer. It goes into your body, it gets filtered through, and it gets accumulated in the thyroid, and then that causes cells within the thyroid gland to mutate, and then you get thyroid cancer. So don't just say radiation causes cancer. You should be more specific. You should say it causes thyroid cancer. It was eventually contained, and so they built a containment dome that went over the entire reactor building to attempt to kind of control the radiation. This shows you some of the spread of the radioactive fallout from Chernobyl. So it's right here. The prevailing winds here kind of go in a bunch of different directions, but I was telling you it went here to Sweden because we're kind of very far north, and so the prevailing winds are more east to west. And so it went, and the radiation detectors outside the nuclear plants in Sweden detected the radiation, and they knew it wasn't their plant. And so they knew that something had happened somewhere else. They were friendly with Finland. It wasn't there. So they knew it was probably somewhere in the USSR. And that was what the first real indication that there had been an accident in Chernobyl. And it kind of gathered, you can see where it was highest. And then finally, the third one that you should know is Fukushima Daiichi. This was in 2011 in Japan. So this is a nuclear power plant. Japan is an archipelago. So there, in this case, it was on the coast of the ocean. And so you can see in this picture, it actually is a picture of the tsunami. There was an underwater earthquake, and it caused a tsunami that overwhelmed the plant. And the pumps, because it was so full of water, the pumps stopped working. And that would be the pumps that pump this water through this system. And so there was no coolant going into the reactor core. And so there were explosions and fires, and 3 of the reactors actually melted down. And so it's been another big meltdown disaster, although I think Chernobyl is probably responsible for more radiation being released than Fukushima. You can see here, this is showing how a lot of the radiation was released out into the Pacific Ocean. Then here, the science behind the story, 570, 571. This is about health impacts from Chernobyl and Fukushima. You can see this little boy here being tested for thyroid cancer. So they've got this detector up next to your thyroid gland is in your throat. All right, now going on to, well, why are people so concerned about nuclear power? The spent fuel rods are the #1 reason that people don't like nuclear power. They're stored at each power plant. So here they're showing you wet storage. This is while they're still pretty hot. And so they're stored in underground pools. And you can see this guy is standing here and he doesn't even really have a ton of protective equipment on. It's not very radioactive in this location. And then dry storage is after they leave the wet storage, when they've cooled down, they get encased in concrete in these big cylinders. And I talked to you guys, I think, about how the long-term storage was planned for Yucca Mountain in Nevada. And the reason for Yucca Mountain was that it was away from large population centers. So it was kind of here in Nevada, and there weren't it's not a lot of people there. It was not seismically active, and the storage could be deep underground in tunnels, is what they were planning on doing. But, like I also told you, they have not yet taken any nuclear waste to Yucca Mountain. Like I said, a lot of people don't want it on the highways. They don't want it passing through their state. And Nevada at the time, like for a long time, I don't know if they do yet, still has they have no nuclear power plants themselves. So they're like, why are we going to store everybody's waste? We don't even have nuclear power. So it's all stored on site at every nuclear power plant. And then this is just kind of showing you about a small modular reactor, which I think is kind of ideal, and I wish we could move that way. This would be just neighborhood-sized reactors distributed across the country so that you don't have one giant nuclear power plant that is, in danger of terrorism or explosions or things like that. You just have small ones scattered all across the landscape. Okay. The next conventional alternative is bioenergy. Another word for this is biomass. And so it's talking about what are some of the things that we use. We burn wood, we burn charcoal, we burn manure. And then they talk about crop residues, forestry residues. So if you do logging and there's all that sawdust when they cut them, you can burn that sawdust. You can burn waste from human power plants. They do that some in Europe. So there's all sorts of biomass that gets burned for energy and electricity purposes. And all of these are kind of delineated on the next 2 pages. So it talks about waste products, bioenergy crops, combustion strategies, scales of production, and so on. So what are some of the things that we do? So here it kind of shows a person, you know, for thousands or maybe millions of years, this is what people did, right? We collected firewood and we had small fires and things like that, hunter-gatherer type societies. And then it kind of shows you a large scale situation, and that's really where we've moved to now. So I got a lot here. So what do we mean for biomass and how can we use it? Biomass can be used for automobiles. If it is used for automobiles, it's called a biofuel. Mainly it's in the form of ethanol. So here it shows corn grown for ethanol, and it's a guy and he's like just looking at his corn. Some vehicles are called E85 or flex fuel vehicles because they run on 85% ethanol and 15% gasoline. So sometimes you go to the pump and it tells you like it might be up to 10% ethanol. That means it's still over 90% gasoline. These vehicles are actually the flip-flop of that, and they use more ethanol than gasoline. There are some problems associated with it. It seems like, oh, great, we can make gasoline out of corn and all our problems are solved. But that is not true. There are some problems with this. It has driven the price of corn up across the world, and corn is a major food source in many countries. Latin America and Africa, they use a lot of corn as a major nutrition supplement, and so it's driven the price of corn up, which is actually causing hunger and famine because farmers would rather sell their corn for more money to ethanol producers than to people to eat. And so that's a problem. And also, it doesn't save much in CO2 and air pollution emissions because growing the corn uses a lot of fossil fuels. You've got all of the tractors and things like that that have to be run to grow the corn. And then it has to be taken somewhere, and it has to be trucked somewhere, and then it has to be turned into ethanol, and all of that uses a lot of energy. So you're really not saving much in the long run. And then you should also know that in Brazil, instead of corn, they use sugarcane for their biomass and turning it into ethanol. It's just an alternative way of doing things. Then in terms of other types of transportation, big engines like trucks and things like that, there is something called biodiesel. Biodiesel is made from used cooking oil. And you can buy conversion kits if you have a diesel car. And I've known some people who have bought some old, like a Volvo diesel or something like that, or Mercedes diesel, like an older one, and done a conversion kit to convert it to biodiesel. And this cooking oil is actually recycled from restaurants. And so if you can get a deal with some restaurants where they will save you their old cooking oil because they have to change it out every so often and put in fresh oil, you can just put that in your biodiesel engine and burn that instead of gasoline. There are less emissions. It's non-toxic because it's food grade, and it is biodegradable because it is an edible type of, cooking oil is usually made from canola or corn or something like that. But I've also heard that it kind of smells funny, like when you're driving, it smells like fried food, which I don't know, maybe that you'd be into that. Okay, so you should know about biodiesel. Another alternative source here from biomass is this idea of algae. Algae can be a source of biofuels, and not only can they be used to convert, into a fuel source, but as they are growing and reproducing, they are absorbing CO2, so that can combat climate change. Although a recent article came out and said that ExxonMobil was abandoning their algae biofuels. So I don't know what the future of algae is going to be. One other type of bioenergy that you should know of is switchgrass as an alternative to corn ethanol. Switchgrass is like a prairie grass that grows on the prairies, and it grows really fast. It's less intensive to grow than corn. It doesn't take as much fossil fuels and things like that, and it provides a lot of cellulose that can be turned into ethanol, and so then it is kind of an easier, more economical way to produce biofuel. So people are looking into that and maybe a switch, which would be good because that is not a food crop for people. So corn could go back to feeding people. And then the last section is on hydroelectric power. We talked in the last unit a good bit about dams and things like that. And so we'll just kind of look at this picture really quickly. But this is a normal kind of hydroelectric dam. You dam up a river, and then behind it, the water will start to rise and you'll get the reservoir. And then you have this still water. And so then it will go from the top down this, tunnel, this pipe or whatever, and it will spin the turbine will spin the generator, and the generator will make electricity. Same as always, only in this case, you're just using gravitational power to have this water flow down this pipe. And then you have the outflow down here. It's cheap. One of the main things is that we don't have any new locations to make dams. So all of the dams that are out there have been there for a while. A lot of dams were built in the 30s with the Civilian Conservation Corps and groups like that. And so most of the dams that are out there are paid for. So the only thing that we really have to pay for in dams is their upkeep. We're not paying on, the cost like a mortgage type situation. You should know how this works, and you should know that we've basically dammed up all the rivers that are any good for being dammed up. Then you have this other thing that is basically almost like a individual house-sized hydroelectric power. So you have like a house or something that might be on a river, and you just have this sort of little inlet here. And then you have a pipe, and so the flowing water, some of it will just naturally flow into here, and it'll run this way, and you can use it. Some water is removed from the river, water passes through the pipe or the channel, and it will spin a turbine in your powerhouse, and it'll generate electricity. It's not going to make a lot, but it might be enough for your home or for your business or something like that. And then that water is returned to the river. So it doesn't ever really leave the pipe. It just spins the turbine and makes the electricity. So this is like what's called personal hydropower. Some things you should know about hydroelectric power: there's no air pollution, there's no greenhouse gas emissions. But we can't expand in the US, like I said, because there's no more good sites. One problem with it is that in tropical countries, you got that reservoir back behind it here, that's still water, and still water breeds mosquitoes. More mosquitoes lead to things like malaria, yellow fever, dengue, Zika, all of those sorts of mosquito-borne diseases. So they're not really always a great solution in tropical countries. There are some new dams that have been built, mainly in Asia. China built an enormous one called the Three Gorges Dam, and it is actually releasing a ton of methane, because if you think about this picture here, back behind this was like a river valley, and there were trees and vegetation and all sorts of things. And so when this reservoir came up over top of it, suddenly that becomes an anaerobic environment, and all of those flooded plants and trees and everything behind the dam are now decomposing in anaerobic conditions, which causes a release of methane. So new dams actually are kind of bad for the environment because of all this methane being released, and methane is a worse greenhouse gas than CO2. So that's the end of chapter 20, which was basically nuclear power, biomass, and hydroelectric.